Thank you for that introduction, and thank you all for coming this afternoon. So my talk, Applications Monday, students bring their real-life control systems experiences into the classroom. The Applications Monday thing, somebody told me I needed a catchy title on this, so this assignment always happens on Monday in my class, and it's about applications, so there you go, there's Applications Monday. Students bring their real-life control experiences into the classroom. When I was asked to do this talk and started thinking about where I wanted to go with it, I thought, what better way to introduce this topic than to have a former student of mine actually bring their real-life experience to this talk as well. So, to get us started today and kind of frame where we're going with this talk, I have invited Evan West to come show us his talk from my class last spring with his drone.
Right, so you all probably know what this is or have heard of these at this point. It's a drone. And I have a video here of... Your mouse is on the other screen, so click. Yeah, I noticed. So I have a video here of me flying this. Hopefully it won't play in like potato quality the whole time. But basically these are very simple systems mechanically in that there's only 4 moving parts. It's all 4 propellers. But there's a lot going on under the hood electronically, and more specifically, what keeps the whole thing stable, because inherently it's not a stable platform. If you just applied power to all these motors, it wouldn't just sit there and hover, is a PID controller. And that runs on this tiny little board. On this board, there are 3 gyros and 3 accelerometers, and a processor running a PID controller. And so what that allows this quadcopter to do is take feedback from the gyroscopic and accelerometer inputs and be able to fly. Now, it's kind of interesting in that when these first came out, they were pretty slow to respond. You couldn't fly acrobatics like what's going on behind you. And part of that reason is because between this control board and the motors is a speed controller. This is what actually controls the motors. And that introduces some latency and other things into the system. Nowadays, the algorithms running on this have been tuned to compensate for that and almost anticipate that lag, and you get a really responsive system. Now, the cool part about these is it's not just buy a board, plug it in, and fly. You can do that, but you can also go in there and actually tune each of the control loops. And you do that by just adjusting the values for the loops like you would in a lot of other systems. And in this video, if you watch at a couple points, you'll see the quadcopter kind of shudder like this. That's because my, I believe it's the D gain, or I gain, is incorrectly tuned, and it's allowing oscillations into the system. And so basically, the other thing going on here that these boards have to take into account is interference, because you've got 2 different radio systems going here. You've got your control system, which is a 2.4 gigahertz link, and that's what controls the drone. But I'm flying this first-person view through this camera, so I've got this dorky-looking thing on my head, and I'm flying through a screen in here. And this is a 5.8 gigahertz control link between these 2 weird-looking antennas. And so they've also had to do a lot of work to filter out interference on these control boards so that the drone doesn't go haywire. And that's kind of my real-life example of a control system. So, thank you.
A little bit of background on where this came from. So now we're back to the boring part here a little bit, but kind of describe where this came from. So when I started here in 2016, I sat in on Dr. Peters' version of this course, and she had a trip to go to and said, hey, can you take over the last lecture of the term and tell them what you had done in industry and how it connects to the class? And so I did that, and in order to encourage these students to actually show up to that particular lecture, she had them write a 1-page summary of what I said to make sure they actually showed up and paid attention to what I said. And we saw a couple times in those papers at the end students saying, wow, I didn't know how this class applied to real life until I heard Dr. Reck's, well, actually I wasn't Dr. Reck at the time, Professor Reck's talk. And so I started thinking about that, and Diane and I talked a little bit about different anecdotal evidence that we had. I also had experienced, as I was TAing for a very similar course in grad school, that students have a really hard time sometimes connecting control systems to real life, even though they haven't inevitably encountered one by the time they're juniors and seniors in college in the US. And so I was sick of seeing this anecdotal evidence of students being confused, and a lot of math goes on in the control systems classes, but they don't really see it. So I wanted to come up with a way to help them make connections between the theory that we were learning in class and real world applications that went beyond the lab. Because at least when I was an undergrad student, sometimes the lab seemed a little bit contrived scenarios, and maybe they didn't quite get there. And I realized our students at Kettering are very unique in the fact that every 3 months they go off and work and have even more experiences with control systems than the average college student probably does. So I started brainstorming different ideas on where to go with this, and making sure that they can make these connections between models, analytical solutions, which are heavily done in math, and these equations into real world scenarios, which is a transition that I struggled with. My job at Rockwell Collins was designing control systems for the real world, and these trade-offs and uncertainties were a huge deal to me. I couldn't make something perfect. It very much was a Facebook scenario of done is better than perfect when you're trying to get an airplane to fly at sea level in Florida in the summer and at 50,000 feet in the cold air, thin air as well. So how do I bring this into the classroom? So as an engineering education researcher who had taken a college teaching class in my PhD, decided to actually go through the literature and look at evidence-based practices, design a new assignment for when I taught dynamic systems with controls, and then I've now gone through 7 iterations of this particular assignment, and I have done some assessment, reflecting, and adapting, which brings us back to some of our principles of effective teaching. So some of the things that I found in literature start with deep learning happens when you can connect what you are learning with what you already know. Hopefully what you already know is accurate. That's a whole different talk in that perspective. And one of those ways to make those connections is a mind map, which is what I've illustrated up here, with control systems at the center, and then the outer ring of bubbles are things that a student may have encountered before coming into the class that this particular class is built off of. So an HVAC system is a really common system that a lot of people have interacted with. We all have a thermostat in our house or apartment that helps us control the temperature. That is one of the most common ones that students encounter before they get to my class. And then the class itself is built on simulation topics, physics, differential equations, and their dynamic systems 1 course. And so there's a lot of background knowledge that I want to build upon in order to cover what I need in the course. But for the novice learner, it has been shown that it's really hard for them to draw a diagram like this and make those connections on their own. They need some facilitation for that. The next thing I started to look at was motivation. So there are a couple popular theories for student motivation. The first one here I have illustrated as expectancy value theory, which basically states that a student's motivation will increase when they expect to succeed and when they see value in the assignment. So I built upon this one expectations. I have very clear expectations, which again draws us back to our principles of effective teaching. I have about a 1-page handout that I give before I set this assignment about what my expectations are for the presentation they're going to give and the write-up. And then looking into value, one of the ways to create value is to connect this to their future selves or their future lives. And so I felt like, from reflecting on those initial statements, that they didn't see value in the course. So if I could create this connection to something they already knew, maybe that would be easier for them to understand the value and how they could use this going forward. So this was theory from Wigfield and Eccles, was another one of the ones that I drew upon. And then the other theory I have from DC and Ryan is self-determination theory. and it basically says that your motivation will go up if your psychological needs are met. And your basic psychological needs as a human are autonomy, relatedness, and competence. Autonomy is pretty straightforward. You want to have some control over what you're doing. So in this particular assignment, I have the students pick their topic. That gives them autonomy. Competence, they want to be able to demonstrate that they actually have competence or understanding of a particular topic. So by sharing this example with me and their classmates, they are demonstrating their competence for the topic and what they have learned, since this is a end of the term sort of assignment. And then finally, relatedness. They want to feel connections to their classmates and their professor, and that their professor in particular is invested in their needs and their success. And so by helping some students through the assignment, because some students have a hard time coming up with an example, I am showing that I am invested in their success in this assignment as well. So those are the sort of underlying theories that went into the design of my assignment. The other thing that I looked at is just assignment creation in general. And Svinicki and Mikichi talk about the difference between high stakes writing and low stakes writing. To put this in context of where it comes in the term for my students, they are in the middle of working on their final project when I give them this assignment, which is very much a high stakes writing assignment. I'm grading on grammar, mechanics, organization, and the readability of a final report. And so I don't want to put emphasis on the writing formality of this particular assignment and add to that stress level at the end of the term. I want this to be more formal, informal, and more about making the connection to a real life example than on the writing and the presentation from that perspective. So since they're already working on high stakes, I try and focus on low stakes writing in this particular assignment, which goes back to also setting expectations for the assignment and making sure that students realize it's more about making a solid connection to the class and being able to articulate the terms of the class as it relates to their assignment, rather than focusing on grammar and so forth. So how did this assignment actually end up? What I ended up with is two different parts. It is in overall a take-home quiz effectively in my class. It includes a written description, which is 7 of the 10 points. And this is, I say, roughly 1 page, double spaced, so it's not long. This goes into the low stakes writing piece of it. But they are supposed to describe an application that they have encountered at some point in their life and connect it back to something in class in that written description. And then on the last day of class, which is where Applications Monday comes from, because Monday is always the last day of my class, I have them give a short in-class TED-style type talk where they have, like Evan demonstrated at the beginning of the talk, a video playing potentially in the background, but they're talking over it. They're not just letting the video do the talking. They are doing a little bit of presentation themselves, and in that way, connecting for the rest of the class, which I really appreciate that last day and the sharing of the rest of the class, because now we have 30 more examples that I didn't even think about being presented to everybody in the class, sharing, and in some cases we have similar examples that we can compare and contrast and spark conversation at the end of class. I make the in-class presentation only 3 of the 10 points because I know I'm already going to make them make their final presentation later in the week, and I do have some students that are deathly afraid of in-class presentations, especially live ones, or are just at this point done with the term and could care less about those 3 points. So I make it entirely up to them. And again, going back to the low stakes part of the assignment and focusing on the written or the connections in class. So now we have 30 extra examples in class. They've all made a connection to something that matters to them. And even if they don't do the assignment, I do have a handful of them that don't do the assignment, but they still show up to class. They still see those examples and learn from them. So after I did this analysis, after about 4 or 5 terms of teaching the class, across the top here are the 3 major topic components of my class. I have system modeling and simulation, frequency response and filtering, and then control systems. I allow them to pick examples from anyone. Obviously, system modeling and simulation is my lowest frequency there. I haven't had that one covered in every term. Most of the examples, as evidenced by the statistics here, are in control systems. Some of those examples include anti-lock brakes, adaptive cruise control, 6-axis robots like the ones on my dress, CNC machines, HVAC, power steering, seatbelt controls. Most of these are co-op examples. I have had examples from hobbies. Last spring, I had a student, in addition to Evan and his quadcopter, I had a student who makes jewelry with metallurgy and works with a kiln a lot. So she talked about how to keep temperature up in a kiln as part of hers. So when I introduce this topic, I know that some students, A, have not encountered examples in their co-op, or B, might be protected by non-disclosure agreements and can't use an example from their co-op. So I allow them to do hobbies. So I've had a lot of motorcycles or other student projects come through as examples. The other bandwidth of cassette tapes, I had a couple audio type people, music synthesizer, sensors from Crash Test Dummies, so I've had examples come in from other classes as well, which I'm totally okay with. Senior capstone, one term they were building 3D printers in their senior capstone. There's lots of controllers and 3D printers, so they bring that example over into the class. And then finally, if they still can't come up with anything from their co-op, from a hobby, from another class, I send them over to the library and say, we have an entire collection of IEEE, SAE, ASME papers and magazines. There has to be something out there that you can find in the library or on the internet. I also have my stack of control systems magazines and things sitting in my office, and so I do occasionally have students come in and grab some scholarly literature as a source. So there's plenty of different options for them to find a connection and bring it into class, and I've had a variety of examples come through. One of the examples, this is just a quick video from one of the first robotics competitions. I had a student bring in this video because I believe at the time they were a mentor for one of the first robotics teams here on campus. And so the autonomous mode for any first robotics project has a ton of controls in it. So I've had first robotics examples. Another example that I've also had in class was the CNC machines. This particular one is a plasma cutter cutting steel. So lots of industrial applications. At this point, you might be thinking, okay, we're Kettering, we have a lot of automotive co-ops. How many times have you got repeat topics? The answer is surprisingly only twice have I had two students show up to the same section with the exact same application and not be able to come up with something new to say. I've had similar topics like the 6-axis robots, but they end up with different applications. Like one's doing something on the line and the other one's painting, so that actually generates a discussion topic that we can actually talk about how we might tune those different depending on the application and what they're doing. So I've actually been pleasantly surprised on the lack of duplication, and in some cases, we've actually ended up with really cool, similar examples that spark discussion and have been a discussion point in every one of my classes since. For example, one term I had a student who worked for GE and talked about the temperature controls of the oven in your kitchen. And in the same term, I had a student who worked in metal curing and manufacturing and talked about an oven for curing steel. Both on their surface are ovens that need to control temperature, but have very, very different control schemes, because for us, when we heat up the oven in our kitchen, what do we do when that bell goes off? We open the door and let all the heat out. So in that particular case, we design the controller to overshoot. We don't care if it goes up to 450 degrees if we set it up to 400, because we're going to let a bunch of heat out to put our pizza or cookies in. Or we're almost to Thanksgiving, put our Thanksgiving turkey in. But otherwise, in the oven for curing metal, there's actually really tight tolerances, and in those cases, you don't have the right properties if the temperature varies more than 2 degrees from its set point for very long periods of time. So while they're both ovens and while they're both controlling temperature, creates a really great discussion in class about requirements and design for control systems. So the other thing that I did, because this was low stakes writing, I wasn't emphasizing scholarly writing, citations, and sources. I also wanted to look at where my students were getting their examples when I went back and looked at these. And it turns out most of them were not getting them from scholarly sources. Over 4 terms, I only had about 5% of them that actually used what I would consider a scholarly source, like a conference paper or a journal. From that perspective, about 2% of them used another course. This was before spring term when I had a lot of them doing controls work in their capstone, so that's probably gone up. About 10% of them used a hobby. About 26% of them used an internet source, but they weren't Wikipedia for the most part. They were something like WikiHow or How Stuff Works or some kind of DIY type sites, but still a little bit, wouldn't say crap from a resource perspective, but they at least probably were on the right track technically. And then about half of them do come from co-op. But the point of this and where this analysis came from, I presented this topic at the American Society for Engineering Education annual conference earlier this year, and I wanted to demonstrate to the rest of the engineering education community that this assignment really isn't dependent on the fact that we have co-op, because only about half of my students have actually used a co-op example, and I feel like it is transferable from that perspective if you don't have everybody doing co-op every time. Some other results I wanted to see, are my students actually achieving the learning objective, which is to make this connection between class and real life? And in spring of 2016, 97% of the students got a 6 or higher on this quiz. That percentage went down after that because I started dropping a quiz. This is the last quiz of the term. They're all really busy in 11th week. And I have students that get to 11th week and say, I'm really happy and I don't want to present. And so they drop this particular quiz. But I still am in the 75 to 85% achievement rate, which from most metrics perspective, if you're getting 75 to 85% of your students achieving a learning objective, you're probably in a pretty good place. And I don't actually have the statistics, but some of the rest of this 15 to 25% of the students actually do still show up to class on that last day. I actually have more students who don't turn it in still show up than I have students who just turn in the paper without presenting. So I feel like I'm actually probably closer to 90 or 95% who at least have heard all of the examples in class. So I feel like overall from an achievement perspective, this assignment has been a pretty good success from that perspective. Some of the unexpected takeaways from this assignment were the conversation starters and the similar examples like I've already talked about with the 2 different ovens, and how those examples carry forward for me and giving me more of a variety than my aerospace examples that I have from my industry experience. And the really cool thing for me is the aha moments I see from the students. So some of those same students who wrote in that assignment, they didn't understand how it connected to the real world. I've had conversations in office hours with students that get these really awesome aha moments where they don't fully appreciate how this class connects to real life until I've had this conversation with them. For example, I had one student come to me and say, I don't have an example from my co-op. I'm like, okay, what do you do in your co-op? This particular student was working with HVAC systems at a pharmaceutical manufacturing company and hadn't quite put together that the temperature control, humidity control, and everything else that they had to do to make that pharmaceutical manufacturing plant appropriate for that purpose was in fact all examples from the class. I pointed them to ASHRA's website, which is the professional society for HVAC folks, and they were able to come up with some really awesome information about how their co-op was entirely control systems and hadn't actually made that connection. Now that we're 1.5 years into AutoDrive, I've had students bring in AutoDrive examples on top of the ones that I've had. And then I've had students also go off in a different tangent because they're thinking about going to medical school or for biomedical applications, and intentionally take this assignment as a challenge to go find an example in a topic that they're really passionate about, which I think is also really cool from that perspective, is finding those connections. So the basis of this assignment and the basis of where I went with this talk is that connections to previous material and previous knowledge, as well as motivation for the topic, are going to increase learning and deep learning from that perspective, and the takeaways from the course. And I have, over now 7 terms of doing this assignment, seen evidence of this throughout the assignment and the examples that I've gotten in class, and I've been really happy with it. So with that, thank you all so much for being here.